Welcome back to Introduction to Probability and Statistics. This course is designed to give you a clear and practical understanding of the most important concepts in probability and statistics without getting lost in unnecessary details. In this lecture or video, we focus on discrete probability distributions. So far, we have covered concepts such as probability, random variables, and how we can find their expected values, including the expectation of a random variable, variance, a standard deviation, moment generating function in the previous videos. And now we want to go a little bit more into details of several cases of discrete distributions. And then in the future video, we discuss continuous distributions. Let's get started. So in this case, we focus on two classes of discrete random variables. The first one is Bernoulli, which models a single trial or experiment with two possible outcomes. If you recall, when we have a random experiment, we have something called a sample space, which is the set of all possible outcomes. And in this case, we have two possibilities. We can think of these as different outcomes. One way is, for example, saying whether we have success or failure. And if the probability of success is P, then the probability of failure using the complement rule is 1 minus P. But we can also think of these as more like binary questions. Is this true or not? Is this yes or not? Do we have, let's say, enough evidence to accept something or not, right? So these are all questions that fall within Bernoulli random variable. Now, the key thing is that for Bernoulli, we have a single trial. If we have now multiple trials, and these trials are independent, now we can extend this to binomial distribution. So binomial is the extension of Bernoulli to n independent trials, each with the same probability of success. Okay, so what is a Bernoulli experiment? A Bernoulli experiment is a random trial that results in one of two possible outcomes, such as failure or success, yes or no, true or false. We can also think of these as tossing a coin, right? We see heads or tails, so it's a binary or Bernoulli experiment. And in this case, if we assume the probability of success or probability of yes or the probability of true is P, that means that the other probability must be 1 minus P. Also, the random variable that we use here, since we only need two possibilities, we usually assign to outcome success 1 and failure 0. Because if you think about it, a random variable is a function that assigns values, numerical values, to outcomes of a random experiment. So in this case, we have success and failure. So we have a mapping. So anytime we see success, we get 1, failure, we get 0. So in order to show the probability mass function for this, we actually have a very simple trick. We can write this as p to the power of x, 1 minus p to the power of 1 minus x. And this works because x here is 0 or 1. So if x equals 1, then we get p to the power of 1, which is p. And the second term vanishes because we get in the exponent 1 minus 1, which is 0. And any number to the power of 0 is 1. So that exactly tells us probability of x equals 1 is p. And then if you plug in here x equals 0, then you actually get 1 minus p, right? Because that's the one that gets exponent 1 minus x, and x is 0. So 1 minus 0 is 1. So this is extremely helpful when you're working with the Bernoulli distribution to know that you do not need to write this as a step function. You can just say that, well, it's only one equation, p to the power of x, 1 minus p to the power of 1 minus x. So now we can look at some of the things that we discussed before based on the expectation or expected value of a random variable. But we want to do this in the context of Bernoulli distribution. So what is the first moment of Bernoulli? E to the expected value of x. So that's a summation over possible outcomes, in this case 0 and 1. And then you multiply the specific value or observation times the corresponding probability. So 0 times probability of x equals 0, and then 1 times probability of x equals 1. And so in this case, we only care about probability of x equals 1, which is p times 1 gives us p. And you can do the same strategy, you use the same strategy to find the second moment here. So to find the second moment, we want to find expected value of x squared, which means that each corresponding value will get raised to the power of 2 and then times the corresponding probability. And remember, in this case, 1 squared is the same as 1. So this means that e of x squared is the same as e of x, which gives us p. But there's no problem here because now we can find the variance, which is the second moment minus the first moment squared. So we get p minus p squared, which is p times 1 minus p if we factor p. Something to keep in mind is that when we find this p minus p squared, we may be worried that this is a negative number. But remember, p is less than 1 or technically less than or equal to 1 because it's a probability. And for values between 0 and 1, when you square something, they become actually smaller, right? So p minus p squared is never negative, and that makes sense because it's a variance of a random variable. But what does this form tell us, right? So as we said, the expression p times 1 minus p is non-negative for any value of p in the interval 0 to 1. So we can use Python or other scientific computing libraries that we have, and we can plot this function p times 1 minus p as a function of p. And this makes a lot of sense. The max variance happens when p equals 0.5, right in the middle, and the variance actually equals 0.25. And you can see that if we have a random trial where p equals 0 or p equals 1, then we know that almost always we get, success or failure, and there's not much variance or variability. So the variance is maximized when we are most uncertain, which is this p equals 0.5. Okay, so now let's look at the binomial experiment. So a binomial experiment is a Bernoulli experiment which is performed independently n times. So the probability of success on each trial is the constant p, right? That's the parameter p that we had before. And the random variable here equals the number of successes in n trials. And therefore, we can, in this case, talk about the number of ways that we can select x positions from n positions. So this second x here should be n. So we have a total of n locations, and we want to select x of them and see how many ways we can do this. So this is what we, use n choose x. That's the notation for that. And actually we have a formula for this, which is n factorial over x factorial times n minus x factorial. And if you're not familiar with this notation, n factorial is basically multiplication of all integers from n to 1. So if you have like 2 factorial, that's 2 times 1, 2. 3 factorial, that's 3 times 2 times 1, which is 6. And also by definition, we use 0 factorial to be 1. So therefore, these are the different number of ways that we can select x positions from n locations. Based on this, then we can write the probability mass function or PMF of this binomial random variable. So the probability of x equals x, and a small x here is the specific realization or observation, is n choose x times p to the power of x, because think about it this way, we have n locations, x of them should be all like successes or yeses, and so that's the probability p, and we multiply them because they're independent. And then the remaining n minus x locations, they're all failures. So that should be 1 minus p, and we multiply these n minus x time. And x can be anywhere from 0 to n. And therefore, we usually use this notation BNP. So n is the number of trials, and p is the probability of success for one trial. And in this case, we get these random variable that can be anywhere from 0 to n. And the nice thing is that if you're, for example, working with Python, you can this is already implemented, so you don't have to write down this equation. That's part of SciPy package, scipy.stats. And when you say binom.pmf, that's the probability mass function. K is the number of successes, so we want to know the probability for that number. And then you have n, total number of trials, and then you have p. So in this next slide, you see the visualization here, where we have the total number of trials set to be 20. Probability of success is 0.5. So you can see that the values that we get are from 0 to 20 on the x-axis, and we can look at the corresponding probabilities for this probability mass function. And you can see that obviously the max happens at 10, right? Because that's the most likely case if you have 20 experiments and the probability of success is 0.5. To get more information about this, let's go first and analytically find the mean and variance of binomial distribution. The nice thing about binomial is that it can be written as the sum of n independent Bernoulli random variables, meaning that this binomial x can be written as x1 plus x2 plus xn, and all these xi's are Bernoulli with p of xi equals 1, which is p. And now we can use the properties of expectation, including linearity of expectation, and the formula that we had for variance. And we can use that here because we know that these random variables are independent. So e of x in this case is e of x1 plus e of x2 plus e of xn. Each of these is p because that's the expected value of a Bernoulli, and you have n of them, so we get n times p. And the variance is also sum of variances, so we get n times p minus p times 1 minus p. And so that's just kind of like, finalizing this slide. So, for different classes of discrete random variables, once we have the probability mass function, and that's usually what you are given in most cases. So somebody gives you a form of the PMF or probability mass function, and then you can plug into the expected value and then find the first moment and second moment and find the variance. But something I want to use to wrap up this video is that if you look at this probability mass function that we have here, it has this bell-shaped curve, meaning that it looks very symmetric around 10, and it has this nice decay on both sides. So if you look at the continuous counterpart of this looks very much like the very famous and well-known Gaussian or normal distribution, but that one is actually a continuous distribution, which we will cover in the next video. So that's something to keep in mind, that it seems that there are some connections between binomial and normal distribution, which we will officially introduce in the next video.